In this podcast, we're going to talk about gas stoichiometry. When you're looking at a balanced equation, if all of the reactants and products are gas and they're at the same conditions of temperature and pressure, or STP, then the mole ratios of our gases are going to be the same as the volume ratios, okay? So let's talk about this a little bit more. So if we were to balance this equation, this would be a 3, and there would be a little imaginary 1 there, and this would be a 2. Now that's standard for any balanced equation. Oops. All right. Now, if you were to look at the mole relationships here, you see that for any balanced equation, the number of moles is going to be the same as the coefficients in front. So we know we'd have 3 hydrogens, 1 nitrogen, and for some reason I kept hitting that button, 2 ammonias. All right, sorry about that. All right, now just because these are all gases, and that's what makes this a special type of stoichiometry, we can apply these same mole ratios to liters as well. So we have 3 liters of hydrogen, 1 liter of nitrogen, and 2 liters of ammonia. So let's see this in practice in some other problems. So here's the same balanced equation. Go ahead and balance it. We have 12 liters of hydrogen, and it wants to know how many liters of ammonia, which is NH3, that we have. So we can just simply use the ratios from our balanced equation to go from liters of hydrogen to liters of ammonia. So we have 3 liters of hydrogen for every 2 liters of ammonia. Okay? All right, so if we work this out, do the math, we would see that that's 8 liters of ammonia. All right, let's look at a different problem. All right, in this one, we see that we have 50 grams of potassium chlorate, that's this, and it wants to know how many liters of oxygen gas we have. Well, because we're at STP, that means that the special molar volume applies, which is 1 mole, is 22.414 liters of a gas. So this applies because we are STP. Now, of course, we need to balance this equation. So we're going to put 2 here, 2 here, and a 3 there. We are starting with 50 grams of potassium chlorate, and you would need to find the molar mass of potassium chlorate by taking your potassium, which is 39.1, plus the chlorine, which is 35.453, plus 3 oxygens, and they're 16 apiece, and you need to get that all out to the molar mass. I've already done that for us, so I got 122.553 grams. All right, and that is equivalent to 1 mole of potassium chlorate. Okay, now we're trying to get to oxygen, so we need to get our mole ratio from our balanced equation. So we got 2 moles of the KClO3 to 3 moles of oxygen. All right, now we're not done yet because we've still got to get to liters of oxygen. And this is where our molar volume, 22.414 liters, comes in. All right, and then we would multiply across the top, multiply across the bottom, divide those answers, and we get 13.7 liters of oxygen gas. Okay, now this last question is a little bit different. I'm going to go ahead and balance our equation. We see for this one, we're still wanting to find liters of oxygen gas, but now we're not at STP. Well, because we're not at STP, we're going to have to use a different equation. We know we want liters, which is volume. We're given temperature in Celsius, but we know no gas law we've used so far has dealt with Celsius. They've all dealt with Kelvin, so we'll do 37 plus 273. And that will give us, let's see, 310 Kelvin for our temperature. And we've got a pressure of 0.93 atmospheres, and we've got this amount of potassium chlorate. We don't see anything changing here, so that tells me that we are going to be using the ideal gas law equation, which is PV equal nRT, to solve this one. Alright, so first we need to get all of our variables worked out. Looks like we've gotten everything straight except for the N, the moles. Okay, so we need to get our 50 grams of potassium chlorate, 2 moles. And we saw from the previous slide the molar mass of potassium chlorate was 122.553. Okay, and when we work that out, we get 0.408 moles. Okay, now we can go plug this into our equation. So our pressure is 0.93 times V, which is what we're trying to find, equal to N, which is 0.408, times R, which is 0.08206, and then our T, which was 310. Alright, when we work out this side, we get 10.37, and that is equal to 0.93 V. So we're going to divide by 0.93 on both sides. Okay, and that gives us our volume is equal to 11.1 liters. Okay, so if you are not at STP, you must use PV equal nRT. If you are at STP, you can assume 1 mole is equal to 22.414, and you can do straight volume calculations. If every single thing, reactants and products, are all gases, then their mole ratio, their coefficients in front, are also their molar volume coefficients, or their liters. Okay? And that's all you need to know to solve gas stoichiometry problems.